In the introductory lecture on superconductivity, I have told you that the superconductors are basically of two types, and these two types of superconductors are called type 1 superconductor and type 2 superconductor. Actually, depending upon the behavior of a material in an external magnetic field, it is decided that the superconductors are of two types. In fact, it is the fact that how strictly the materials follow the Meissner effect, that is the key parameter to decide the type of superconductor. And on this basis, we see that the superconductors can be classified into two classes, and those two classes of superconductors are simply known as type 1 superconductor and type 2 superconductor. We will also learn that actually this type 1 superconductors are also called soft conductors, superconductors, while the type 2 superconductors are also called hard superconductors. Why they are called soft superconductors and hard superconductors, what is the reason behind this, we will also learn in this lecture. But before knowing the different characteristic of type 1 and type 2 superconductors, first of all, I would like to introduce you the concept of critical field and critical temperature, because this critical field and critical temperature plays a very important role in deciding the behavior of a material in external magnetic field. Okay. So let us first of all see what is the critical field and critical temperature and how they are related. Okay. In fact, in 1913, a famous scientist who was invented actually superconductivity of mercury, Camillin Owens, actually he observed that a superconductor regains its normal state below the critical temperature if it is placed in a sufficiently strong magnetic field. Critical temperature means the temperature below which a material behaves as a superconductor. So in his experiment, Owens found that when a superconducting material is placed in a magnetic field and the strength of magnetic field is increased, then at a particular value of magnetic field, after that particular value of magnetic field, the superconducting behavior get lost. Okay. Actually, when you say that superconducting behavior will get lost, it means the material will not behave like a perfect diamagnet, because you have learnt a Meissner effect that a superconductor exhibits perfect diamagnetism. So when you say that superconductivity has been lost, it means the diamagnetic behavior of the material has been lost. So actually we define this critical magnetic field in this way: the value of magnetic field at which the superconductivity vanishes, that is called actually the threshold or critical field, and it is denoted by the symbol Sc. So when the applied field H will be greater than or equal to Hc, okay, H is greater or equal to Sc, then the material loses its superconductivity, or you can say that the superconductivity is destroyed, and so the diamagnetic behavior of the material will also get destroyed, or you can say that Meissner effect will not then followed by the material. So in this way we define this critical magnetic field as the field at which the superconductivity becomes zero, it vanishes. Okay. But this critical field is actually related to the temperature. Its value is different at different temperature. In other words, you can say that the critical field actually changes with temperature. Okay. So it's the same material will have different critical magnetic field at different temperature. Okay. So how this Hc is related to the temperature, we will see here. In this graph, actually you can see that I have shown a typical plot of critical magnetic field versus temperature for a particular metal lead. Okay, and you can see from this figure that when temperature T is equal to 0 Kelvin, then this critical field has the highest value or maximum value, which I have denoted by this symbol Hc0. Hc of 0, this represents the critical field at 0 Kelvin temperature. Okay, and you can see as the temperature is increased, the critical field actually decreases somewhat in parabolic nature or parabolic manner. Okay, and finally you can see that at this temperature Tc, which is actually the critical temperature for this lead, the critical field vanishes, critical field becomes 0. Okay, so between this temperature 0 to Tc, you know, the material will behave like a superconductor. But when a temperature will be greater than this Tc, okay, then it is in the normal state. So actually the left region of this curve is the superconducting region, and the right upper region of this curve is actually the normal state of the material region. Okay, so you can say that the superconducting state is stable only in some definite ranges of magnetic fields and temperature. Okay, for higher fields and temperatures, the normal state is more stable. Okay, and this graphical plot where you can see that the critical field varies with temperature is somewhat in parabolic manner. Actually, this graphical plot is also known as magnetic phase transition. Okay, magnetic phase diagram, you can say. Okay, and as the curves are almost parabolic, so in mathematical way, if you want to relate the Hc at any temperature T with temperature T, then you can use this empirical relation. This is actually an empirical formula based on the experimental data. Okay, so at any temperature T, the critical field is given as Hc of 0. Here Hc of 0, this is actually critical field at 0 Kelvin. Okay, and T is any temperature on which you are finding this critical field, and Tc is the critical temperature. Okay. Now you can see from this result, due to the presence of this factor T square, the variation is almost parabolic. Okay, and if you you can see that if we take T equal to 0K, okay, then it is clear that this Hc is equal to Hc of 0. So at 0 Kelvin temperature, this is the value of the critical field, which is actually the highest value of critical field. Okay, and when T is equal to Tc, it is clear from this result that T over Tc will be equal to 1, and 1 minus 1 will be 0. So at temperature Tc, the critical field simply vanishes, And it is evident from this figure. You can see here T is equal to Tc, and actually this critical field becomes 0. Okay. Now it is also obvious from this result. If T is smaller, then you will subtract from 1 some a smaller number. Okay. And so you will get a larger value. So you can say from this result it is evident that for a smaller temperature Hc has larger value. But as the temperature T increases, the value of this critical field decreases. Okay? And finally, at T equal to Tc, it becomes 0. It becomes 0. So, this is the relation between the critical field and the critical temperature. One thing I would like to say you, in some of the standard textbook, I have seen that this result is written like this: Hc equal to Hc of 0, 1 minus T over Tc. But I think this relation which is found in most of the standard textbook is not correct. Because if Hc is related to temperature by this relation, then the graphical plot of Hc in against of T must be equal to a straight line, because this is equation of 1 degree and it is equation of a straight line in the form y equal to mx plus c. But as experimentally it is found that the variation of Sc in against of T is in the parabolic fashion. So definitely here there should be T square, not T. So as in some of the standard textbook we find that Sc is related to T by this relation. I think that is not appropriate relation. That is not in accordance with our experimental result. But this is actually a empirical formula based on the experimental result. So you must write this relation. Okay. So I think now you have an idea about the critical field and how this critical field is related to the critical temperature. Okay. So in nutshell, you can say that critical field means the field above which the superconducting state vanishes and the material becomes a normal material. Okay. Now, as I have told you, our prime aim of this lecture is to discuss the two types of superconductors, which are called type 1 superconductor and type 2 superconductor. Actually, this classification is based on the fact that how strictly the Meissner effect is followed by our material. Okay. On that basis, we classify the material in two classes, that is type 1 superconductor and type 2 superconductor. Okay. So now let us see what are the basic features of type 1 superconductor, which is also called soft superconductors. Actually, when you talk about the type 1 superconductor, that means the superconductors which strictly follow the Meissner effect. Okay. So you can define the superconductors which will strictly follow the Meissner effect will be called actually the type 1 superconductor. Okay. When you say that this superconductor strictly follow Meissner effect, it means there will be no penetration of magnetic field into the surface of the superconductor if it is of type 1. Okay. Now, how in magnetic field this superconductor will behave? For this, I have shown here a typical graphical plot of magnetic behavior of lead, which is actually a type 1 superconductor. Okay. In fact, you can see a graph has been plotted between the minus M. M is the magnetization, and with its negative value is plotted in against of the magnetic field. Okay, and the magnetic field has been taken here in SI unit, that is kilo ampere meter inverse, and this M is also in kilo ampere meter inverse. Okay. Actually, you can see from this figure that when H is equal to 0, then the magnetization is also 0. Okay. But as the magnetic field is increased, the magnetization increases actually in the linearly with this H, but in negative direction. So in this case, it is found that this M is proportional to H. M is proportional to H. And this M is equal to minus chi H. Actually, here this minus sign implies that the direction of the magnetization developed in this material is just in opposite direction of the magnetizing field. And this is actually the behavior of a diamagnetic material. Okay? And this magnetization in negative direction increases linearly up to when the magnetic field becomes equal to the critical field. Okay? And you can see when at this point, corresponding to this point, the magnetic field is equal to the critical field, that is H is equal to Hc. Okay? And when H becomes equal to Hc, you can see this magnetization is just magnetization abruptly falls to 0. Abruptly fall. There is an abrupt fall. Okay? And after that, this material behaves as a normal conductor. So between this H equal to 0 and H equal to Sc, up to which this M is varying linearly with H, this state of the material is the superconducting state, and it behaves just as a perfect diamagnet, and the Meissner effect is strictly followed. Okay. So actually all these things I have written here. You can see that these superconductors exhibit perfect diamagnetism below this critical temperature Sc, as you can see. And this Sc has actually a value of the order of 0.1 Tesla, which is not very large, 0.1 Tesla for most of the cases. Okay. Now you can see, as the magnetic field is increased beyond this Hc, as you increase the magnetic field, the field penetrates the material completely and later abruptly reverts its normal resistive state. Okay. And so these materials give away their superconductivity at lower field strength of the order of 0.1 Tesla. And that's why such a materials are called soft superconductors. These are called soft because the critical magnetic field is very small for such a material, and it maintains its superconductivity for a small range of magnetic field, and actually its superconductivity is lost. Okay. When the field strength is not very large but small. That's why we simply say that these materials can be called soft superconductors. So these are also called soft superconductors. Okay. Actually, you can see that the pure specimens of various metals exhibit this type of behavior. So you can say that a large number of pure metals are examples of type 1 superconductor. Okay. Now, these materials have very limited technical applications because the value of Sc for it is very small. Due to the smaller value of critical field for this material is not of great practical importance, and so its technical applications are very limited. Okay. So whenever in practice we use the superconducting material to make any device, generally this type 1 superconductors are not used. Okay. So these are the basic features of type 1 superconductor, and I think now you have a clear-cut idea of this. Actually, this type of question will be asked you in your examination, particularly in short answer type question. Write a short notes on type 1 superconductor, type 2 superconductor. Then you have to write the answer in this way. So actually what I have explained, I have mentioned all those things here, and you can note down these things in your notebook, and that will be a very good notes. Some of my viewers always ask me to provide PDF on Google Drive, but I would like to say that after watching my video and after noting all the facts of my video, there will be no need of PDF of these lectures or these videos, because my videos are already in the PDF form. Everything I have written here, and that can be directly written by the viewers in their examinations. Okay. So let us see. I have written here that these semiconductor exhibits perfect diamagnetism below the critical field, as you have seen. You can see below this critical field, this material behaves like a superconductor. Okay. And as the applied field is increased beyond Sc, the field penetrates the material completely and later abruptly reverts normal resistive state. Okay. These materials gives away their superconductivity at lower field strength and referred as the soft superconductors. Okay. Already I have explained these things. Pure specimens of various metals exhibit this type of behavior. Okay. And these materials have very limited applications owing to the very low value of Sc. Okay. So these were the basic facts regarding this type 1 superconductor. Now we will talk about type 2 superconductors, which are also called hard superconductors. Okay. Actually, when you say type 2 superconductors, actually these are the superconductors which do not follow Meissner effect strictly. Mark it. When you have defined this type 1 superconductor, what we have told? You have told that the superconductors which obey or which follows Meissner effect strictly, those superconductors are called type 1 superconductor. But if the superconductors do not obey Meissner effect in a strict sense or strictly, then such superconductors are called type 2 superconductors. Okay? It means when you say that these superconductors do not obey, do not follow Meissner effect strictly, what does it mean? It means the magnetic field does not penetrate these materials abruptly at the critical field, as was the case of the type 1 superconductor. You can say, see that when H is equal to Sc, beyond this Sc, magnetic field penetrates into the material abruptly. But you will see, in case of this type 2 superconductor, the magnetic field does not penetrate into the material abruptly at the critical field. Okay? This is the basic difference. And how type 1 and type 2 superconductors behave differently from one another in magnetic field. For this, now let us see a graphical plot of the negative of magnetization in against of the magnetizing field H, and this curve has been shown for the PbBi-Ly, that is lead bismuth Ly at a particular temperature 4.2 Kelvin. Okay, 4.2 Kelvin. Now see this figure. You can see here that when H is equal to 0, the magnetization is 0. Okay, you can see. And as H increases, then this minus M increases. M is actually directly proportional to H when H is smaller. Okay, and when you will actually remove this proportionality sign, this will be minus chi of H. Chi is magnetic susceptibility, you know. This minus sign here also shows that M is developed in the opposite direction of the magnetizing field. Okay, and this is the behavior of a diamagnet, as you know. So when H is increased, M increases, but in negative direction. Okay, and this increment of M takes place until H becomes equal to this Hc1, mark it here, Hc1. Up to this, M varies linearly with the magnetic field. And so this region between H equal to 0 and H equal to Hc1, I have marked this region by 1 in this figure. Okay, and actually this region 1 is the superconducting state. Mark it. The region between H equal to 0 and H equal to Hc1. This is called region 1, as I have marked in this figure, and this is called the superconducting state. You can see. Now, as the field increases from this Hc1, then the magnetization does not fall to 0 abruptly, but it decreases smoothly with increase in H. And when H becomes equal to Hc, see the figure here, H becomes equal to Hc2, then M becomes 0. See the difference. In case of type 1 superconductor, you have seen that after this value of Sc, this is actually the value of Sc here, you can see this is Sc, and when H is increased after Sc, the magnetization abruptly falls to 0. Okay, but there is no abrupt fall of magnetization in case of this material. Okay, so you can see that that the curve for the fields less than Hc1, the material exhibits perfect diamagnetism. Okay, and no flux penetration takes place. Okay, and so you can say that for H less than Hc1, H less than Hc1, the material exists in superconducting state, and I have marked this state by 1 in this figure. Okay, but as the field exceeds this Hc1, you can see the flux begins to penetrate the specimen, and for H equal to Hc2, see here, the complete penetration occurs and the material becomes a normal conductor. Okay, so you can see the region between H equal to Hc1, that is, you can say that Hc1 is less or equal to H, and this is less or equal to Hc2, which I have actually marked in this figure by region 2. You can see it here. This region is actually called vortex or mixed or intermediate state. Okay, In fact, this Hc1 is called the lower critical field and Hc2 is called the upper critical field. So in case of type 2 superconductor, there are two critical fields, lower critical field Hc1 and the upper critical field Hc2. Okay? And the state of the material between Hc1 and Hc2 is neither a pure superconducting state nor a normal state, but it is a mixed state. It is a mixed state. So the diamagnetic behavior of the material vanishes gradually, not abruptly in this region, and the flux density B inside the material has a constant value, not zero. So B is not zero, and so you can say that Meissner effect is not obeyed. Okay, it means Meissner effect is not strictly followed in this region. Okay. In fact, as I have told you that the specimen in this region between H equal to Sc1 and H equal to Sc2 is said to be existing in the vortex state, or you can also say it as a intermediate state or a mixed state. Okay. Actually, this state of the material has a complicated distribution of superconducting and non-superconducting regions, and this may be regarded as a mixture of superconducting and normal conducting states. Okay. In fact, the type 2 superconductors are also called hard superconductors. These are called hard superconductors. Why they are called hard superconductors? Because relatively large fields are needed to bring them back to the normal state. Okay? As you can see, this region third, which is beyond this Hc2, the upper critical limit, H greater than Hc2, this region is marked by region 3, and this is called normal state. And you can see, to bring the material in the normal state, we need a very strong magnetic field, and therefore these materials are called the hard superconductors. You have seen in case of type 1 superconductor, a very small magnetic field is needed to bring the material into the normal state. But in case of type 2 superconductor, a strong magnetic field is needed to bring the material into the normal state, and that's why such materials are also called hard superconductors. Okay. Apart from this, large magnetic hysteresis can be induced in these materials by appropriate mechanical treatment. And you know from the study of magnetism, the materials which are actually have actually high magnetic hysteresis law, those are actually hard magnetic material. So on that analogy, due to the large magnetic hysteresis which can be induced in these materials by the appropriate mechanical treatment, these materials are called hard superconductors. Okay? And hence these materials can be used to manufacture superconducting wires which can be used to produce high magnetic fields of the order of 10 Tesla. And apart from some metals and alloys, the newly developed copper oxide superconductors belong to this category, and this material has this upper limit of the critical field which is equal to 150 Tesla, which is very high. Okay. So these are the basic features of type 2 superconductors, or you can say the hard superconductors. And again, for your convenience, what I have explained by the help of this figure, I have noted down those things, and so you can pause the video, note down these things in your notebook, and that will be very helpful for your examination purpose. So just now, what I have explained, I am just giving a reading of those things. You can see all those things I have already explained. These superconductors do not follow Meissner effect strictly. That is, the magnetic field does not penetrate these materials abruptly at the critical field. Okay? You have learned this. The typical magnetization curve for PB/Ly has been shown, and that illustrates the magnetic behavior of such superconductor. Okay? And it is clear from this curve that for the fields H less than Sc1, the material exhibits perfect diamagnetism and no flux penetration takes place. And thus, for H less than Sc1, the material exists in the superconducting state. And as the field exceeds Sc1, the flux begins to penetrate the specimen, and for H equal to Sc2, the complete penetration occurs and the material becomes a normal conductor. Okay? All these things we have learnt already. The fields Sc1 and Sc2 are called lower and upper critical fields respectively. Okay? And in the region between Sc1 and Sc2, the diamagnetic behavior of the material vanishes gradually and the flux density B inside the specimen remains non-zero. That is, the Meissner effect is not strictly followed. The specimen in this region is said to be existing in vortex or intermediate state or mixed state. Okay? This state has a complicated distribution of superconducting and non-superconducting regions and may be regarded as a mixture of superconducting and normal state. Okay? Now, for example, apart from some metals and alloys, the newly developed copper oxide superconductors belong to this category, and this superconductor has the upper critical field about 150 Tesla, which is very high. And so these materials are of immense practical importance. Okay? So I think now a clear-cut idea of the basic feature of type 1 and type 2 semiconductor is definitely now in your mind. Okay? Thank you very much.